That's it. Good afternoon, everyone. So this is going to be a very quick flash talk, mostly a research talk. And the whole idea is to take a step back and really think about what are we capturing in terms of the analysis we do. So that's why the talk is titled Beyond Hypnograms, Assessing Sleep Stability. So till now, from last 2 days and today's talk, you would have gotten a fair idea of how we do sleep analysis and what all parameters we use as a descriptive summary of the sleep. And if you remember from Dr. Sanjeev Sinha's talk, bulk of the results he presented were dealing with micro architecture of the sleep. So grossly, when you look at things, there are no obvious patterns between a clinical group versus a control group. But when you zoom in and look at certain patterns, that's where you see the difference. So in my current talk, I am planning to give you a few glimpses of some limitations of the sleep, the polysomnography technique per se, the way in which we conventionally use it. And since we are basic scientists, our job is to go beyond hypnograms. So let's get into the talk. So I would want you to meet 3 different hypnograms from the normally, so the so-called control subjects. So this is from, say, subject A, subject B, and subject C. Now, I want all of you to take a quick look at these hypnograms and tell me which subject A, B, or C. Let me this right. So is it subject A, subject B, or subject C who will have the highest sleep efficiency? So you can use your chat box to quickly tell us whether highest sleep efficiency will be for A, B, or C. We'll just wait for maybe 30 seconds. You can quickly put it in the chat box, whether it is A, B, or C, who is having the largest sleep efficiency. Okay, many of you are telling B. B is having the largest sleep efficiency. Any other options? Right. So one thing is, I'm wondering why you didn't opt for A and all of you were favoring B, A maybe. Anybody in favor of C? I think bulk of the polls are towards A and B. So now quickly let me reveal what the hypnogram analysis as per ASM manual say. As per ASM manual, if we calculate, subject A has only 86% sleep efficiency, subject B has 91% sleep efficiency, and subject C has 84% efficiency. So rightly, all of you pointed out that subject B will have the largest sleep efficiency. You are right as per ASM, but now I want you to closely focus on hypnogram. If you look at subject A, that person was having a very good sleep, very small sleep onset latency. Only once that person woke up in middle of the night, and somewhere deep late into the sleep, maybe 2 a.m. or so, he woke up, maybe he would have gone to washroom, and that person took a very long time to fall asleep. And then once he fell into the sleep, it was more or less stable sleep. So I use the word stable sleep, but what you see, the first number conveys sleep efficiency, second number conveys the arousals, the wake onsets in between sleep. So if you look here, this person had only woken up 8 times in between and they were all short bouts. If you look at subject B, even though that person has a very high sleep efficiency, look at the number of times that person woke up, and at times you can see the person spent in wake time for a very long period. And one more thing is, look at the sleep stage transition. So this person woke up 36 times, and look at this hypnogram, the person C. That person woke up 48 times in between. Even then, the person has a very high sleep efficiency. So I want to really focus in on the point. So when we talk about sleep stability, sleep quality, instead of looking at single numbers, if we have a composite score which takes into account different aspects of sleep, for example, how fast you can go to the sleep, can you maintain a very stable sleep in one state instead of going back and forth, even though it's between N1 and N2, instead of shuffling between the states, can you maintain a single bout, longest streak in one particular state? Or do you call that a better sleep, right? So there are many aspects which are not taken into consideration in the way we assess hypnograms. And this is really of concern when we want to understand sleep in the so-called normal people. So there are many research which is now pointing in the direction before they manifest clinical symptoms, maybe 1 year, 2 years before they start showing their clinical symptoms, their sleep started getting deteriorating. But it will not manifest in terms of the macro sleep structure, but the essence, the deterioration lies in the very minute, the so-called macro sleep architecture. So this is the motivation to look beyond hypnograms and see what happens. And one minor point, this was published in the Journal of Clinical Sleep Medicine, recent issue, the overall underscorer agreement between 5 technologists. So mind you, these are the technologists who are well trained to score the hypnogram as per all the rules. Even then, they agree only up to 75%, max 80%. That means 20% of the data, where say I would have marked it as stage N1, but another equally qualified, talented technologist would have labeled it as stage N2 or REM or wake or whatever. So this is a challenge in the overall aspect, because the starting point of all analysis is sleep staging. We get the polysomnographic data, 8 hours of 9 hours of data, and we are converting that rich data into a running sequence of hypnograms. Then we quantify percentage of sleep stages, duration of sleep stages, so on and so forth. So we have challenges in terms of this, where the actual measures, they quantify different aspects of the same thing, but we do not have a single score which takes into account multiple things and give a composite score, right? So that is one aspect. And the second aspect is in the individual variability in the sleep. And we are studying sleep in a lab setup. And even though we keep one night as an accommodating night, where we make sure that the subject is really comfortable with the environment. So one of our previous studies, we were lucky enough to study the same subject across 4 nights. And bulk of these people were staying with us in campus, and they were properly rested. Then only we took them for our study. Irrespective of that, I want you to focus on a couple of people where, for example, if you take this particular subject, the pale green color, first night, second night, third night, excellent sleep efficiency. For some reason, fourth night sleep efficiency fell down to 76%. And so steady, then falling. Some other people you can see, they vary a lot. They started with a okayish type of sleep efficiency. Second night was way better. Third became way down, see 63%. And fourth night was also in the same state. So you cannot attribute this fall in sleep efficiency, day by day variability, because the environment is new. It's same for all of them. It's just that each person is different. And if you look at different nights, we see a different pattern. So the entity we are trying to study, the sleep itself, is having huge variability. So we can't afford to study a person for 7 consecutive nights. And which night will you pick? Will you pick the best night? Will you pick the worst night? And even some research groups have tried to quantify the variability. So some people who are able to, even though they sleep, their sleep efficiency might be poor, for example, 75%, but on a daily basis, they maintain that sleep efficiency. Compared to some people who one day sleep at 90% sleep efficiency, another day slightly lower. So how do we deal with these things, right? And in the way, the conventional sense, the sleep efficiency is a very crude score, and it is very tricky to interpret scores which are above 80. For example, if a person is having a sleep efficiency of 85%, 90%, 92%, it's not really monotonic. We cannot tell that a person having sleep efficiency of 92% is a better sleeper than a person having sleep efficiency of 85%. And sleep onset latency. As per ASM manual, the time taken by the subject from lights out time to the time the person hits any sleep stage, that duration is considered as sleep onset latency. But I want to propose this hypothetical scenario where the subject goes to N1 sleep for one epoch, then he is back to wake. As per ASM manual, still the latency will be only short. But just because after the stable one epoch of N1, which is very unstable, the person is spending long time in wake, which is never captured in the metric we quantify, right? And again, the percentages, durations, all these are kind of very gross measures. If our goal is to compare it with the clinical population, yes, it makes sense. But if we want to study just the control people, these measures in the way it's conventionally used might miss out on so many aspects. That's the point we are trying to score. And there is no composite score which takes in multiple aspects of the sleep. For example, we know that sleep happens in cycles. It's not a monolithic entity from lights off to lights on. It advances with cycle and cycle dynamics changes. So we know that the REM duration, REM depends towards the later cycles. And where is that getting captured in the conventional hypnogram analysis? So it is, you can allude to this cartoon where the different hypnogram measures, they are capturing one aspect of it. But it will be absolutely wrong to tell that elephant is like a broomstick or elephant is like a pillar. So what we want when we want to talk broadly as a concept of sleep stability and use that framework of sleep stability to interpret any findings which comes out of a hypnogram, we should go beyond hypnogram. So if you read, I think after chapter number 100 of the sleep medicine book by Dement, they talk about some of these measures. So the whole idea is, how do we conceptualize capturing sleep stability? One is we can talk about sleep continuity. So long awakenings, arousals, mean duration of awakenings, these are indications of sleep continuity. And there are other measures which talk about sleep stability per se, stage transitions, and again, whether if the person is spending, say, 10 epochs N1, 3 epochs N2, 2 epochs of N3, again N1, N2. So that is like happening in bouts. It's not happening as a streak. So we can calculate what is the longest time duration the subject has spent in N2 sleep, right? So that captures sleep stability. And again, sleep organization, number of cycles, total cycle time, within cycle parameter. So instead of analyzing the sleep parameters from lights off to lights on, we break it down into different cycles and capture all the normal parameters, percentages, durations, or whatever, and analyze the sleep data in terms of cycles. So this is called sleep cycle level analysis. And some of our previous work have done that, and it has really added more intuition to what's actually going on, right? And even there are better parameters. For example, there is something called latency to persistent sleep. So that is time elapsed from lights out to first 10 consecutive minutes of sleep. So instead of sleep onset latency, if we keep counting until the person has reached the stable sleep, so that is LTPS, then there is something called latency to unequivocal sleep. So instead of stopping it at N1, you calculate the time taken by the person to go till a stable sleep. So N1 is a very shaky stage compared to N2. So you wait till the person hits an N2 and count those many minutes. And again, quantify sleep transition. So transition from lighter to deeper stages, they are an indicator of better sleep. But when you reach a N3 stage, and then again you roll back to N2 or N1, as per ASM or sleep efficiency parts, still you will get a very high score. But the moment you start calculating sleep stage transition, deeper to lighter, lighter to deeper, this will give us extra understanding and intuition. Again, I touched upon the sleep cycle-based analysis and the longest chain of N2, longest chain of N3. Interestingly, all these parameters are mentioned in the standard textbook, the sleep medicine principles of sleep medicine textbook. But it is indeed sad that these suggestions doesn't reach the ASM manual, where the technologist or somebody who is scoring the sleep would have never heard about these terminologies, even though it comes in a very standard textbook. And then there is something called functional instability period. So this is when N1, N2, N3 alternate between each other, so that if you observe for 10 minutes, you can see all the stages. So it is interpreted as the inability of central nervous system to maintain stable sleep stages. And apparently there is this paper from Conte et al., where they talk about when people age, the functional instability periods increase. So there are some people who still have a very good sleep efficiency, but their periods of functional instability becomes more and more, right? So all these things are mentioned in chapter number 161 in the Principles and Practice of Sleep Medicine. And the conventional way in which we do sleep analysis, nowadays we have so many improved tools and methods. So one is we can run some automated analysis. Somebody was talking about it, and it can mark wherever the algorithm detects spindles. And whenever we score the sleep data, we can rely on these measures also. So instead of, again, it's visually scoring is the gold standard, but nothing is preventing us from using extra tools, add-ons to improve our sleep scoring. And this is something called spectrogram. So across the night, we can look at the frequency distribution, and you can clearly see whenever it is stable end-to-end entry, you see a very clear slow wave pattern. And the moment the person's transition to a wake or a REM-like state, it disintegrates. So visually, it's very easy to pick up these things. And when you look at sleep scoring, it is very difficult to score the transition. When a person is transitioning from REM to wake, those are the epochs which are very difficult to score. So why not use these methods which are already available and which will help us in improving our sleep staging efficiency. And there is this lab from Harvard, Pre-Rao lab. So this lab, the goal of this lab is to come up with methods which will boost the way we do sleep research and sleep analysis. And they run a course every year, and all their codes and other tutorials are freely available. And another amazing tool is called YASA from Rafael Vallat. So as a lab, we are huge fans of this particular package. YASA is called yet another spindle algorithm. So it's an automated way to identify spindles, and it will highlight the spindles. And now once the spindles are detected, you can quantify the spindle. What is the mean frequency? What's the duration? What's the amplitude? Is it symmetric? So you can get tons of parameters. Again, it's not fully foolproof. It needs manual supervision to get it right. But nevertheless, just because the huge manual labor involved, some of these tools will help us to really get into these details, the micro architecture analysis and all. So now let's quickly change gears, and I want to quickly show you what lies beyond hypnogram. So PSD technique need not be conceptualized as a passive technique. What we want to capture is the dynamic aspect of the sleep. Sleep is very rich in its patterns and all compared to wake sleep. So all we get is a single night. Imagine the scenario. We recruit a patient or a subject to the study. The person is going to spend one night in the lab, which is a different environment. It's not their natural environment. And you have all these sensors, wires, whatever. Irrespective of all those things, can we add some extra things to polysomnography technique, which will help us to capture some parameters which are indicators of sleep stability? So that was one motivation to go from a normal static analysis to capture a sleep profile. So a profile typically will have so many elements in it, and we are coming to a judgment by considering the entire thing altogether. So can we construct a sleep profile from a single night of polysomnography? That's what we did. At least we took some baby steps in that direction. So this paper was out somewhere in 2019. So we titled it Beyond Hypnogram, Assessing Sleep Stability Using Acoustic and Electrical Stimulation. So the idea was very simple. When people were sleeping, what we did was every 10 seconds or so, we presented random auditory stimulus, which were very mild so that the people will not wake up. So every 10 seconds or so, beep, 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 it will go like that. And initially the people will be wondering what is this beep sound. After that, the brain is used to that. You will never notice the sound of the fan after a while, and they were just sleeping. So sleeping brain is not so sleepy. It can still process information. So there are many papers which talk about when people were presenting their own names versus other people's names, the brain response to their own names were processed better compared to other people's names because it has evolutionary value. Otherwise, why on midnight, 2 a.m., somebody is shouting your name, there is fire in the building or something. So we are all evolutionary beasts or machines. So the way in which the brain wiring, the anatomy, the structure, everything is there, the brain, the sleeping brain does process information. And we were leveraging on that aspect of physiology to study the sleep stability. So what we found out, I will just quickly take a minute to explain this. So whenever we were presenting these beep tones, We cut out EEG around 2 seconds after that. We lined them up after every sound presentation. We did an averaging of all these sounds, and we get something called a ERP wave. So once you average all this, we will get this very characteristic pattern. So it's just ups and downs of a very simple neat trace, and the latency of this and the amplitude, how tall these waves are, it carries rich physiological information. So whether your peak, this particular amplitude is tall, short, it has absolute physiological meaning. And what we found out was we got two different people and they were having same amount of sleep percentages of entry sleep, and which is roughly 22%, 25%. And this particular subject number 1, so when this beep was presented, this particular subject produced this particular pattern, and we call it with some fancy names. For example, negative going wave is called N550, other wave is called P900 because it's a positive going wave. It comes 900 milliseconds after the presentation of the tone. So we just measured the amplitude of these tones and we just documented that for every subject. We did one more thing. We calculated the number of sleep stage transitions these people were having. And interesting enough, what we found out that people having very large amplitude value for this particular N550 P900 complex, they had very small number of sleep transitions, even though they had same amount of sleep entry percentages. So the whole summary was, if anybody having larger values of this N550 P900 complex, they will have very lower non-REM disruptions. So that's a very strong indicator of their sleep stability. And we don't have to do sleep recording 2 days, 3 days, 4 days. And you don't need to do this for a very long time. Even from 2-3 hours of data, even though we ran it for the entire 8 hours duration, we got roughly some 4,200 trials. We did not even need it. Even from just maybe 1 or 2 hours of data, we will be able to find out this pattern, which will talk about their sleep stability, which is not really captured in the conventional hypnogram. So that was one strong motivation. Indeed, it's convincing, and this is one aspect of the study. And there are many other interesting patterns which we can study. And from many other animal studies and invasive studies, it is known that this K-complex, these ERPs, N550, P900, they're early indicators of K-complex vertex waves and slow waves. So imagine like a pupae hatching and becoming a butterfly. In N1 stage, you will see the vertex waves. And as and when sleep gets deeper and deeper, in N2, we will see K-complexes. And if you remember from Dr. Gulshan's lecture, even when you have so many K-complexes, which is occupying more than 6 seconds of the stage, you call it N3. So it's literally vertex waves, they becoming K-complexes, and then K-complexes slowly getting transitioned to slow waves. So there is this generator hypothesis where the circuitry which is involved, it is adjusting itself so that it can manifest it as different patterns and stages. So all these things can be really studied when we look into the microarchitecture analysis, and it tells us a lot about how the sleep progresses, right? So I just want to quickly put it out there, and we can study. I am just putting it there, and this is a final slide. And we can study a lot because many people, when it was conceptualized initially, people are wondering, K-complexes sometimes will lead to arousal, sometimes it will lead to a better sleep stage also. So interestingly, Alfred Loomis in his standard paper, and this is a wonderful paper, which talks about the double role played by K-complex. So in one hand, it will act as a sleep guardian, protector of the sleep. And on the other hand, because of the survival part of the circuitry, when some external input, it should make us go to wake circuitry as well. So it's very interesting that the same phenomena, the pattern called K-complex, it can fork, and one route will lead to stabilizing sleep, other route will result in waking up. So I would want to, so that's a dual role played by K-complex. I didn't touch upon sleep spindles for lack of time. And I would like to end with this final slide where this is a sleep special issue, which came out in October. It's a wonderful article. It's a bunch of articles. And then there is this amazing painting where the person is peacefully asleep, and even though there is a huge threat, a lion coming in, and finally I think the lion decides to spare the person, let the person sleep and go on. Thank you.